Alright, in the last video we discussed about how do we represent any function by a polynomial function, or the Taylor's polynomial of degree n. We denote it by p and x, right? Meaning that we can use the Taylor's formula to find out a polynomial to approximate any function around a point x equals to c, right? So when you find equivalent function for any other function, for example natural log of x or e to the x or sine x, like that. So when we represent those functions by a polynomial function of degree n, so n could be like, you can approximate by p2x or p3x or p4x, p5x, and so on. Okay, so as you take the higher order polynomial, or p, when you increase the degree of p and x, when you increase n, then you will get the better approximation, right? But we do not get exactly the same function, or we cannot find exactly the same we cannot find out a Taylor's polynomial function that gives you the exact same value of the function fx, because we are using the approximation. It will never be the same function as, for example, natural log of x, because if you approximate natural log of x using the p and x, or sine x using p and x, or cosine x, or e to the x using p and x, it will never be exactly the same, because the Taylor's polynomial has infinitely many terms, right? And then so you can never list all the terms in the Taylor's polynomial, because you can take any n there, right? But more terms, or the more degrees on the Taylor's polynomial, is the better approximation for the f of x. But and as I said, it is never exact. Okay, so it is just the approximation, so there is always a chance of error. So in the Taylor's polynomial, the error is denoted by r and x. That is the error. Okay, the error is denoted by r and x. So what is r and x? R and x is the exact function fx minus the Taylor's approximation p and x. Okay, the difference between the exact function fx and then p and x around x equals to c, right? Around x equals to c. Okay, that difference is the error. Okay, now there is a error. There is a theorem for the Taylor's polynomial, or the Taylor's remainder. What it says is, you can basically find out how big the error would be. Okay, so how big or how small, actually the big. Okay, so actually we take how big can an error be. Okay, and then we will also can say how many terms should we take in order to limit the error, or limit the size of the error under certain number. Okay, how many terms, or what degree of the p and x, what is the value of n we should take, so that the size of the error is less than a certain amount. Okay, we can limit that. So this is what this theorem talks. Okay, if a function fx is differentiable through order n plus 1 in an interval I containing c, then for each x in I, this is x in I, okay, there exists g between x and c such that f of x equals to fc. So these first n terms are the p and x. This is p and x, right? And then plus r and x, that is the remainder, where the remainder can be approximated. Remainder can be calculated by the nth derivative. Okay, nth derivative. N plus 1th derivative of the function fx at g. Okay, at g, and then times x minus c to the n plus 1 divided by n plus 1. That is the formula for the remainder. And again, so this formula itself we do not use much, but one of the useful consequence of the Taylor's theorem is you can limit the size of the remainder. You see that? just take the absolute value of these. The absolute value of the remainder is always less than or equals to x minus c to the n plus 1 absolute value to the n plus 1 over n plus 1 factorial times the maximum of that function. Okay, maximum of the n plus 1, the derivative of the function fx at g, where max of absolute value of fn plus 1 g is the maximum value of fn plus 1 g, okay, in the interval x comma c or c comma x. It depends on if x is bigger than c or smaller. Basically it says between x and c. That's what it is saying. Okay, so what it says is basically you can limit, you can find out the limit of the, or you can find out the bounds for the error. Okay, how big or how small the error is, you can basically find out like that. Okay, and then we will see two examples. One example is you will use the Taylor's theorem to obtain the upper bound of the error. Okay, and another is how many terms or what degree of the Taylor's polynomial should be considered in order to get the error less than certain value. Okay, that's these two examples. Okay, let us see that. Example 1, this is a question number, I think this is question number 48 from the book. Okay, from your book, section 9.7. Okay, what it says is use Taylor's theorem to obtain the upper bound for error approximation, then calculate the exact value of the error. So you can calculate the exact value of the error as well. Okay guys, so here on this example what we are going to do here is basically so we assume that we will use the Maclaurin series. Okay, let f of x equals to e to the x. Okay, now if you use the Maclaurin series, meaning that if you use the Taylor's series of e to the x around x equals to 0, okay, then what do you get? Then p, so this is 5x equals to, this is what you will get, 1 plus, okay, x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial plus x to the 5 over 5 factorial. This is around x equals to 0. This is what you get. Okay, this is the question has given that. Okay, now if you replace x equals to 1, what do you get? When you can write c equals to 0, okay, x equals to, let me write down, x equals to c equals to 0, x equals to c equals to 0. Okay, now so this is around 0. This is what the Taylor's polynomial of degree 5. Okay, now if you want to approximate what is the value of e to the 1, then you replace x by 1, right? When you say that you can say like this, you can approximate, so c x equals to c equals to 0, right? Then this is approximation of e to the x. You see that this is the approximation of e to the x around x equals to 0. Since 1 is close to 0, then e to the 1 is basically 1 plus 1 plus 1 squared over 2. I'm just replacing x by 1 here. Okay, plus 1 cubed over 3 factorial plus 1 to the 4 over 4 factorial plus 1 to the 5 over 5 factorial. That's what you get. Okay, this is e to the 1. Okay guys, now so as we said here, you can see that the remainder, okay, so the remainder of this function f of x, okay, because f of x will be, this is p5x plus remainder, right? So the remainder can be less or equals to the maximum of the 6th derivative. Okay, so maximum of the 6th derivative, and then x minus c. What is c? C is 0, x is 1. So that will be 1 to the n plus 1, right? That's what you get. So what is n? N is 5 here. You see that? N is 5 divided by 5 plus 1, 6 factorial, because here we see that n equals to 5 because p5, right? So here n equals to 5. Let me write on that thing, n equals to 5 there. Okay, now what we can write here then is, since what is f of 6x? Why do I need f6, sixth derivative? Because Rn x is lesser or equals to that maximum of 6th derivative. So e to the x, we see that, right? So what is the maximum of, because we see that what it says is where maximum of, so what it says is so n plus 1, then there exists g between x and c. Okay, we will have a g between x and c, but what is x here? X is 1 and then c is 0, right? So we need to find out the maximum of that. We need to find out the maximum of that thing, right? So what we can write is, this is x, so the maximum value of f of 6x equals to e to the x in the interval 0 to 1. In this interval, the maximum value of f6x will be, the maximum value will be, because it is an increasing function. If you find out the derivative of this is x, okay? It is an increasing function, right? So the maximum lies on the, since an increasing function, the maximum value lies on the, let me write on, this is the, I think we should write like that, right? So the maximum value lies on the boundary, right? Because it is the increasing function. In is e to the 1 on the right boundary. So that is the maximum value, right? So what you can write, then by the theorem, then by that above theorem, you can write r5x, okay, which is lesser or equals to x minus c is 1 minus 0. C is 0, okay? So 1 minus 0, x is 1 because we are taking x equals to 1 here, okay? That's x equals to 1. So 1 to the 6, you see that? 1 to the 6. And then times, divide by 6 factorial, right? Times, what is the maximum? Maximum is e to the 1, just e, right? So what do you get? So you get this, if you use calculator for this, you will get 0.00378, because 6 factorial is, I think it is 720. E over 720 will be like that, okay? So this is what you get. So this is the bound. This is actually the bound for the error. Okay, guys. So this is actually the bound for the error. So what will be the exact value, or this is the bound? Okay. What will be the exact error when you approximate this by p5? Okay. So to find out the exact error, what you need to do is you find out this value using calculator, and then plus that, okay? So so you see that, so to find out the exact value, so exact value, let me use different color. So exact value of error, because that's what it says, right? Exact value of the error. So this is what the exact value of the error, right? The error is lesser or equals to that, right? What is the exact value? Exact value of the error is equals to e to the 1 minus that value, okay? So this is e to the 1 is approximated by that value, right? But there are so many terms to come, but we did not write all those terms. So what I am doing is e to the 1 minus that value. So how much is this, this 1 plus 1? Let me write down that. So it will be 1 plus 1 plus 1 over 2 plus 1 over 3 factorial is 6 plus 1 over 4 factorial is 24 plus 1 over 5 factorial is 120. This is what you got, and then minus let's say e to the 1, okay? If I do that, then you got the so it is, so e to the 1 minus 2.71667, like that. And if you subtract that, you will get 0.001. That's the exact value of the error, okay? 0.0016, that is the exact error. When you approximate by P5, and then if you by this, okay, and then if you find out the exact value, it is E minus that is 0.0016. That is the exact value of the error. But when you find out this, when you use that formula, what it says is the error must be less than 0.00378, and what exact error is 0.0016. So this is accurate, right? This says that the error must be less than that, and actually the error is less than that, right? That's what we got. Okay, guys, so this is the exact value of error. All right, so the next example that we want to see here is, I think this is question number 54 from the book. Not 54, it is 51 from the book. Question number 51 from the book. Okay, all right, so how would that look like? So it says determine the degree of Maclaurin's polynomial required for error approximation. Okay, for error approximation of fx equals to sine x to approximate f at 0.3. So what we will do is we have fx equals to sine x, right? So to find out the degree, we will use that technique again. We will use that technique, right? So so what do you get around? So Maclaurin's polynomial. So Maclaurin's polynomial will be just c equals to 0, right? That's what you have. Okay, guys. So whatever degree you find out, because you say that we have Rn x, the absolute value of Rn x is less or equals to x minus c to the n plus 1 divided by n plus 1 factorial, okay, and then maximum of, so you get you don't actually need, because Rn, you can use this formula, okay. Let me use that formula instead of that absolute value thing, okay. So what I can do here is Rn x equals to, I can use that formula, okay, no worries. So Rn x equals to what? Fn plus 1 g, okay, and then x minus c to the n plus 1 over n plus 1 factorial. This is the error formula, right? But you see that for any, since any derivative of fx, because this is n plus 1 derivative, f of n plus 1 x, any derivative of that is less or equals to 1. We know that, right? Any derivative of that sine x will be less or equal, the absolute value, actually the absolute value of any derivative is less, I mean even the non-absolute value, right, which is always less or equals to 1 for all x, not only in the interval x and 0. This is for any values of x, okay. So what is that, what is the x there then, because you want to find out the value of f at 0.3. So c is here, c is 0, and we'll take x equals to 0.3. okay. So what I'm going to do here is, it says that the error must be less than 0.00001, okay. So what I'm going to do is, I'm going to do this guy, okay. So this guy is less than 0.001. But what is that? What is this maximum value of this? So Rn x is less or equals to that, right? And this value will be less or equals to 0.001. So let me write down that Rn x is less or equals to the absolute value of that. What is the absolute value? A maximum value of fn plus 1g will be always 1, because f is sine x, so this is always less or equals to 1, and then x is 0.3, and then c is 0, because it's the Maclaurin series, over n plus 1 factorial, okay, and then 0.3 minus 0 to the what? N plus 1, okay, and this must be 0.001. Okay, guys, so what you get here is basically you get 0.3 to the n plus 1 over n plus 1 factorial, okay, which is less than 0.001. What we do here is, now we take n equals to 1, and then try if you get this is right or wrong. Try n equals to 2, try n equals to 3, and so on. So when you try n equals to 3, when n equals to 3, what do you get? On the left side you will get 0.3 to the 4 divided by 3 plus 1, 4 factorial. That will give you that the inequality is valid. So if you try n equals to 1 or n equals 2, the inequality will be wrong, okay? But when n equals to 3 or 4 or 5, so for n greater than 3, this inequality is valid, okay? So meaning that n equals to 3. So we need P3x in order to use the Taylor's polynomial of sine x to approximate f at 0.3, or Maclaurin's polynomial of sine x, that means around 0, to approximate f at 0.3 with error less than 0.01. That's what we get. Okay guys, let us do one more example of finding the degree of the Taylor's polynomial or Maclaurin's polynomial. Okay, so this question is question number 54 from the book. Okay, what it says is, what degree of polynomial Pnx expanded around c equals to 1 is needed to approximate ln 1.25 so that the error is less than 0.001. Okay guys, so here, so we say that we want to approximate the value of natural log of 1.25. okay, so what we want to do first is let f of x equals to f of x equals to natural log of x. Okay, natural log of x, that is f of x. Okay, so what is f prime of x? You see that f prime is what? 1 over x. What is f double prime? Negative 1 over x squared. You see that? Plus minus like that. So if you continue that, then what do you get? Then you get that f of n plus 1, okay, x is, you see that on the first derivative it is positive 1 over x. Okay, you see that? And then in the second derivative, it is negative, not equals to here, right? In the third derivative it is positive, so and so on. Okay, so what do you get? How do I get the first derivative? If you take n equals to 0, so it looks like negative 1 to the n, you see that, and then n factorial over n x to the n plus 1. Okay, x to the n plus 1. I can show you that n plus 1. How? Because see that f triple prime equals to what? They will get 2 over, okay, 2 over x to the third, and then f iv equals to, you get 6 over x to the 4 but negative. You see that whenever n is 0, that is f prime, that is positive. Whenever n is 1, when n is 1 you will get the second derivative, right? When n is 2 you will get the third derivative, and so on. Meaning that when the value of n is even, then you will get positive, right? That means when n is even means the derivative is odd. For the odd derivative you will get positive values, and for the even derivative you will get negative value. That's what you get. That is f of n plus 1x. Okay, so this is what you get. Okay, now then by Taylor's theorem, what do you get? The Taylor's theorem says that Rn x, the remainder, is equals to what? You get x minus c to the n plus 1, and then f of n plus 1 g, right, divide by n plus 1 factorial, where g is between what? 1 and 1.25. 1 and 1.25. That's what the theorem says, because it is x and c. So okay, c is 1, x is 1.25. That's what we have. This is x. Okay, c is 1, x is 1.25. Okay, then so what we want to do is we want to find out the error of approximation when we are approximating natural log of 1.25. okay, That's what you are approximating 1.25. So what do you get if you do x is 1.25 minus c is 1 to the n plus 1 divided by n plus 1 factorial, right? So what is f of n plus 1? So f of n plus 1 g, you just plug in that value, okay? But if you do the absolute value of Rn, then that absolute value will get rid of that negative 1, right? So you can write n factorial over x is what? 1.25 to the n plus 1. That's what you get, right? 1.25. Oh, not x though. By the way, that is g, right? So let me write down g there. So where g is between 1 and 1.25, that's g, because that was for g, right? So when you replace x by g, you will get n factorial over g to the n plus 1. Okay, now so what do you get? So how much is g 1 over g to the n plus 1? Okay, how much is 1 over g to the n plus 1? But in the interval 1 and 1.25, 1 over g to the n plus 1, any exponent of g is less or equals to 1, okay? Because in the interval 1 over g is how much? So at, you see that, at g equals to 1, okay, 1 over g plus 1 is equals to 1, right? But at g equals to 1.25, it is 1.25 to the power exponent n plus 1. That is bigger exponent, meaning that the whole fraction will be less than 1. So either way, in this interval, that value is less or equals to 1. Okay, so which is less or equals to, you can write 0.25 to the n plus 1 over n plus 1 factorial times you have let's see, there should be n factorial. Since all of these are positive, so I didn't take the absolute value now. Now look at this, 0.25 to the n plus 1 divided by n plus 1 times n factorial, and then there is n factorial. So you cancel that n factorial and n factorial. So basically you got 0.25 to the n plus 1 divided by n plus 1. But the question says that the error must be less than 0.01. So this must be less than 0.001. Now you take n equals to 1 and then see if it satisfies or not. Take n equals to 2 and then see if it satisfies or not. Take n equals to, if it satisfies, stop. If it does not satisfy, then go to the next value of n. Okay, so it does not satisfy, cross it, and it will satisfy. Okay, hence n equals to 1. So you could have done this problem exactly the same way as this one if it makes more sense to you. Okay guys, all right, that's what you do. That's all for this chapter. Okay, thank you.